Welcome to .NET Core for Malware. We're going to be analyzing new opportunities for red teamers presented by the .NET Core platform and showcase practical examples to take advantage of them. Before we get started, I wanted to let you know that I am available for questions right now in the chat as you are watching the talk, so feel free to ask away. Just to quickly introduce myself, my name is Ryan Cobb. I'm a consultant and red teamer at SpecterOps. I tend to focus mostly on software engineering and building offensive tool sets, which has resulted in building some open source tools like Covenant and Sharpsploit, which both rely on .NET Tradecraft. You can find me at my blog or on Twitter. To get started, let's introduce .NET. What exactly is .NET? Well, it's a software development platform that was developed by Microsoft. It includes a large built-in class library and a powerful set of APIs. Originally, because it was developed by Microsoft, it was really only able to run on Windows systems, and it's actually language independent. Oftentimes, .NET is implicitly associated with C#. .NET itself really only defines some specifications that can be implemented by any programming language. Some examples would be the lesser-known F#, and also PowerShell is built on .NET as well. So some terminology when it comes to versioning. The .NET Framework is the original implementation of .NET, which only ran on Microsoft Windows. .NET Core is the newer open source and cross-platform implementation of .NET that we're going to be talking about today. And maybe the most confusing of the terminology is the .NET Standard. Whereas the other two listed here are actual implementations of .NET, the .NET Standard is a bit more abstract. It's just a formal specifications of APIs that a .NET implementation must fulfill in order to comply to the standard. That sounds confusing at first, but it's not too bad. Essentially, when you're writing your code, instead of targeting .NET Framework or .NET Core, you can target a specific version of the .NET Standard, say version 2.1. When you run your application, it can be run on any implementation that complies with that version 2.1 standard, like .NET Core 2.1 or .NET Framework version 4.7.1. Basically, it's a way to target multiple .NET implementations at once and a way to make sure your code is compatible with both. But the .NET Standard is going to be partially abandoned as of .NET 5, and we'll be further analyzing the reasoning for that here in a bit. But as a sneak peek at the reasoning now, the reason is that .NET Framework is going to be abandoned entirely. So once there is no future version of .NET Framework and there's only .NET Core, there's really no reason to maintain something like the .NET Standard that allows you to target multiple .NET implementations at the same time, since there's really only going to be the one .NET implementation, namely .NET Core. A more visual explanation might be helpful to see how all of this pieces together. Starting at the bottom, we have the specifications. The Common Intermediate Language, often referred to with different acronyms like CIL, MSIL, or just IL, is a specification for what a compiled binary has to look like to be utilized inside of a .NET runtime. There are several runtimes built on top of that specification, such as .NET Framework's CLR or Common Language Runtime, as well as .NET Core's Core CLR. These runtimes are often referred to as virtual machines, and what they do is take the compiled IL code, translate it into machine code, and manage that code as it's being executed, which is why .NET is often referred to as managed code. Many different languages can be used to generate the IL code and are built on top of .NET, such as C# and PowerShell for the .NET Framework and C# and PowerShell Core for .NET Core. So the timeline basically works like this. You write some C# code that you compile with some compiler, maybe the one built into Visual Studio, and you get out some exe file, which is a .NET assembly compiled to IL code. When you go to run that executable, at runtime, CLR is going to get a hold of your executable and translate that into usable machine code and manage it throughout the runtime. So we'll start out a bit just talking about the .NET Framework so that you'll have some context for when we talk about .NET Core. So several years ago, PowerShell for offensive operations was all the rage until some defensive visibility features were added. But the problem was that all the visibility features were added in at the language level, specific for PowerShell. Script block logging logs PowerShell code. The AMC integration written for PowerShell examined only the PowerShell code. So an easy pivot for us as attackers was to use another language that utilizes the .NET framework even more directly, like C#. So why do we like to use the C# and the .NET framework? Well, it's installed and enabled by default on most Windows operating system versions, with a few exceptions. There's less defensive visibility in C# than some alternatives like PowerShell, as we mentioned before. Security products are starting to look for C# and .NET stuff, but they aren't quite as good at finding it as they are at things like PowerShell. And .NET has a large set of powerful APIs that makes development a lot easier and faster for us than unmanaged alternatives like C. So we'll use .NET for a lot of the same reasons that ordinary software developers might use it. Again, to reiterate, C# had less visibility at the cost of losing some flexibility that a scripting language like PowerShell offered. However, AMP-C, the anti-malware scan interface, was introduced shortly after into the .NET framework in version 4.8. So we built this large array of .NET tooling and tradecraft, all written in C#. This has largely been pretty successful. I even built a C2 framework called Covenant with the explicit purpose of handling .NET implants and tasks. And I'll reference Covenant a bit throughout this talk. While the talk isn't really a talk about Covenant, a lot of the information in this talk originates from the experience of writing a C2 framework that supports .NET Core implants. The server side of Covenant is built on .NET Core, and originally the implant ran only on the .NET framework until we added the .NET Core implant called Brutes, which I'll refer back to throughout the rest of the talk. All right, with all of that context, let's talk .NET Core. One big reason I'm so excited about .NET Core is that the future of .NET itself is on .NET Core. The next version of .NET, .NET 5, will be .NET Core. At the time of recording this, there's already .NET 5 release candidates. And there's a good chance that by November 20th, .NET 5 will already be generally available. And once this happens, the .NET framework is on its way to being deprecated. So one way or another, we're going to have to start learning about .NET Core as attackers. And I imagine it won't be long before .NET Core will be installed by default on future OS versions. But using .NET Core for malware is a fairly new concept. I haven't seen any public information about it being used in the wild. There's limited information on tradecraft or open source tools, but there's a lot of potential here, and I think it's inevitable before we start to see it in the wild. For us as attackers, we're able to utilize the newest APIs for our malware. If you've done any .NET development for malware, you know how painful it is to limit yourself to .NET 3.5 for maximum compatibility. And there's not a lot of existing research on the topic. Scotty Austin, who goes by Checkymandr, wrote CoreSploit, which is a port of Sharpsploit for .NET Core specifically, and it includes many of the capabilities that were able to be ported over. Just a bit of functionality missing. And there's a blog post from Bohops that found that if the .NET Core runtime is installed, it can be used as an application whitelisting bypass. And that's really it. When it comes to existing research, it's hard to find much outside of that. A few more reasons I am excited about .NET Core. Like I said before, we can utilize the newest APIs. We aren't stuck in 2007 anymore. Just a few examples of the highlights. We get assembly load context, which gives us the ability to load and unload new assemblies, which surprisingly is not possible in version 3.5 of .NET Framework. Version 3.5 was totally missing JSON serialization APIs. You get actual usable asynchronous primitives, which is a huge pain in version 3.5. And I could go on. You get a lot of the newest capabilities that attackers have been limited from using in the .NET framework. .NET Core is cross-platform, so this allows us to utilize our tooling on Linux and macOS without writing a totally new toolset. In some cases, .NET Core is not required to be installed on target systems. So this is actually an improvement over the .NET framework, where not only did it have to be installed on the endpoint, you had to be careful about that the right version was installed on the endpoint as well. And in most cases, it's very easy to port .NET framework code to .NET Core, depending on what you're writing. For example, when creating Covenant's .NET Core implant, Brutes, I was able to take the existing code for the .NET framework implant and convert it with very little changes. This makes it a lot easier to adapt to the new platform. Getting into more of the specifics on .NET Core malware, we're going to dive into a few areas. Visibility, which everyone always wants to hear about, where we'll talk about the AMSI as well as ETW. We'll talk about execution techniques, and we'll touch on a few unique practical problems encountered when developing .NET Core malware and some solutions for dealing with them. So first, let's talk about visibility. When .NET Core was first created, the AMSI, or anti-malware scan interface, was just totally missing. So if you can use an early .NET version, anything before .NET Core 3.0, AMSI won't even be an issue. But unfortunately for us, at least as attackers, .NET Core versioning has proved to be much faster than what we've seen with .NET Framework. So you're really unlikely to see any version of .NET Core for 3.0 installed basically anywhere. But again, with AMSI and any AV solution, at the end of the day, it relies on signatures. There's not a lot of .NET Core malware out there, which means there's fewer signatures. And we also have bypasses. So you might be surprised to learn that AMSI bypasses for .NET Core don't need to be any different than .NET Framework. To explain why, let's take a quick look at how the AMSI works. So the way .NET works is that some application, such as PowerShell, VBScript, are the examples in this image, or in this case, .NET Core, loads up the AMSI DLL into the process and calls functions in that DLL to scan the questionable content, namely your assembly that you're trying to run. So in the .NET Framework, because we always have the privileges to write to the memory in our own process, we can patch out the logic in these functions to always pass these scans. So just based on how the AMSI works, we can do this in .NET Core just as easily as we could in the .NET Framework. Barring some code written by XPN and Rostemaus, this code actually works great in .NET Core as well. So you can see what's happening here is we're calling load library to load up the AMSI DLL. We're getting the address of the AMSI scan buffer function, which the core CLR will use to scan content with AMSI. And we're patching out some key parts of memory of that function. Because we have control of the process, we have the control of that function, and we can bypass the check. The other important visibility source is ETW, or event tracing for Windows. And maybe not surprising at this point, but we can bypass ETW in .NET Core the exact same way. In this case, ETW is utilized via ntdll.dll instead of AMSI.dll. But the methodology here is the same. We're calling load library to bring the DLL into our process, getting the memory address of the correct method in that DLL, and then patching out some key parts of memory to have the function do what we want it to. And again, borrowed this code from XPN and others. Moving on from visibility, let's talk execution techniques. We've talked about how it's unlikely, currently at least, to find a target with .NET Core installed. So how are we actually going to execute our code? A few options. First, if the .NET Core runtime is installed, you're likely to find the .NET Core command line tools, which can be used for execution. Alternatively, we can use some alternative core runtimes that do ahead of time compilation, such as Core RT or .NET Native. In these experimental runtimes, the IL code is converted to native code at compile time. So these binaries look just like unmanaged binaries and can be executed without the runtime being installed. And finally, we have a feature called publish single file, which we'll talk about in detail in just a minute. To start, let's talk about the .NET Core CLI. Whenever you install the .NET Core runtime or the full SDK, you get a .NET command line interface. There's a couple of ways we can execute our malware with the command line interface. First, we can just point the .NET.exe CLI at a pre-built .NET Core assembly, like in the first example. We also can point it at a .NET Core project file. And if we just do .NET run, this will find the project file, build the application, and execute it. This is sort of interesting in that the project file and the executable don't actually appear in the command line arguments and won't show up in the event logs. Now, to be clear, the .NET Core runtime must be installed on the system in order to do this. This is really uncommon for now, so we won't focus too much on this technique, but I imagine it will become more important as .NET Core starts being installed by default, which I imagine could happen at some point this year or next. And just as an interesting side note, the .NET Core CLI was the basis for an application whitelisting bypass technique discovered by Bohops, which you can read about on his blog. Moving on to Core RT. Core RT does ahead of time compilation, and that's not just ahead of time compilation to IL, but actually does the IL conversion to native machine code at compile time. This is sort of strange for a .NET implementation because the resulting binary does not need to actually execute within a runtime since everything is already machine code. So .NET Core does not need to be installed. File sizes can be small for Core RT, which can be important, as this is something we will continue to talk about a lot today. But it's important to stress that Core RT is an experimental runtime for a reason. It's not a production-ready Microsoft product. I don't think it ever will be. Performance absolutely can be affected. Some code might just not work on Core RT, so it's important to actually try it out ahead of time. There's also this thing called .NET Native, but it's closed source, while Core RT is open source and on GitHub. And .NET Native is specifically for UWP, or Universal Windows Platform, which are basically the weird Windows Store apps. But it's a similar concept. But the execution technique I want to spend the most time on is publish single file. So if you've been in the offensive security world for a while, you'll know that living off the land is an important concept for red teamers. That is, the idea that we should only make use of technologies that are likely to be present on the target environments that we intend to attack. But .NET Core is unlikely to be installed by default yet on target endpoints, but doesn't actually need to be in some cases. As of .NET Core 3.0 and beyond, a feature called Publish Single File was introduced. And what this does is compile an assembly and all of its dependencies into a single unmanaged PE executable. The difference between this and Core RT is that your .NET code will still be managed by a real runtime, and the entire runtime will also be embedded into this PE. The PE serves as a simple wrapper that will bootstrap the runtime, which eventually will manage your assembly you've created. So what does this look like? Again, we write out some C# code just like normal, put this through a compiler. You'll actually need to use the .NET CLI's publish command to utilize this feature. This will generate your .NET assembly, which will be stuffed inside of an unmanaged PE executable file, as will the entire core CLR runtime. At runtime, the PE will kick off the core CLR, which will load your assembly and do its normal stuff that converts the IL to machine code and manages it throughout the execution. And this turns out to be extremely useful to us as attackers. .NET Core does not need to be installed on the target operating system at all. However, there are some drawbacks here, primarily file size. If you write a very basic hello world assembly in C# that has very few dependencies and compile that with publish single file, you're going to have a binary that sits somewhere around 60 megabytes, or maybe a little bigger, which is unfortunate. But keep in mind that you are stuffing the entire runtime into the binary. The code itself is cross-platform and can be run on any operating system, but the binary itself can only be compiled for a single target operating system. So you're going to have to generate 3 separate 60 megabyte or so payloads, one for Windows, one for Linux, one for macOS, so that it knows which runtime to embed into the executable. You don't want to have multiple of them in there and make the payload even larger. There's a lot of similarities here to writing Go payloads. You get a large self-contained executable that has cross-platform benefits. So now that we've talked about a few execution techniques, I wanted to talk about a few unique practical problems that are presented for .NET Core malware and how we might solve them. First, as we alluded to, file size can be a problem, 60 megabytes might just be too large for you to feel comfortable using in some phishing scenarios. But I'll add that normal, run-of-the-mill legitimate software can sometimes be a lot larger than even this. So 60 megabytes might actually be fine in a lot of scenarios. The second problem we'll tackle is one of dependencies. Some solutions to the file size problem can actually generate new problems when it comes to delayed dependencies, which we'll talk about in just a bit. So let's talk file size. 60 megabytes is just too big, so what are we going to do about it? A couple of solutions. One is the IL linker. Microsoft has created an illinker.tasks namespace that helps with this problem, and it's easily usable when compiling our single file assemblies with the publish trimmed feature. What this does is trim unnecessary assemblies from our application and even from the runtime itself. So let's say we write an assembly that has no need for the system.diagnostics.process namespace. We don't actually use that API at all. Well, that assembly can simply be removed from the runtime and gets embedded in the executable. This can be a somewhat dangerous process. In some cases, the IL linker might fail to recognize a dependency that you need that will cause your code to fail. For example, if you're using reflection to load a dependency, the IL linker has no way of knowing that and will not include it in the runtime. In addition to the IL linker, we can use CoreRT to reduce file sizes, like we've mentioned before. So let's see how effective this can be. We'll be using Covenant's .NET Core implant as the example here. We do our standard publish single file compilation and land at 60 megabytes. If we add in the IL linker publish trimmed feature, we cut this in half to about 30 megabytes. Now, in Covenant, this is where I stop for brutes. 30 megabytes is certainly larger than I would like it to be, for sure. My guess is that the IL linker continues to improve in size reduction in .NET 5 and beyond. And I'm a little hesitant to make use of an experimental runtime by default, but I'm definitely looking for new ways to cut down the size, and maybe we can introduce CoreRT compilation as an additional option in the future. If we do use CoreRT, with the default settings, we get down to around 5 megabytes, but increasing the CoreRT settings to be more aggressive, we can get down to 4 or even 3 megabytes. I believe there are more extensive options in CoreRT to reduce even further if you are willing to not make use of reflection in your code. But for brutes, at least, it's a hard dependency for now. So that's the file size problem and some practical solutions. If you want to see this taken to a further extreme, I'd recommend this blog post where the author writes a .NET Core snake game and gets very creative to get the file size down to under 8 kilobytes, which is very impressive. Like I mentioned, brutes use the publish single file and publish trimmed features, and we get to about 30 megabytes for the initial payload. What's cool is that even with this unmanaged PE payload, we still can load in additional capabilities at runtime. So if we want to run an LS, once we have an implant, the capability can be sent over the network to the payload and loaded up inside the implant. This is a fairly necessary feature for implants, so I was very excited to find that it is still possible with this publish single file feature. However, the publish trimmed feature can cause us some issues with dependencies when we load up additional capabilities. When we generate these additional capabilities, we don't use the publish single file feature, since we can't just load an unmanaged assembly within our implant. So these tasks are true .NET assemblies that don't contain an entire core CLR runtime. If we trim out dependencies we don't need in our base implant, but then load up capabilities that depend on features that we just trimmed out, we are going to run into problems. As an example, let's say we have an implant and a task that looks something like this. On the right side, you see an implant looping, asking the server side continuously if there are any new tasks. And if it gets one, it tries to use assembly.load to load it up and execute it. On the left side, you see a task that does process listing. To do that, it's using the system.diagnostics.process API. However, this API was trimmed out of our implant because it didn't need it in the actual implant code. So when we go to load and execute this assembly, we're going to get a runtime error that our task can't find the necessary dependency, which is unfortunate. So we have a couple of potential solutions here. The first makes use of assembly load context, which we mentioned for other purposes very briefly earlier on. We can also make use of assembly resolve. So here's how the assembly load context solution works. Checkymandr was the first person to alert me to this potential solution. What he discovered was that instead of directly using assembly.load on the implant side, we can use assembly load context. And before we load the task directly, we load each of the dependencies required by the task using assembly load context.load from stream. In this example, the implant has to change to adapt to the task. And we could automate and abstract this out a bit more, allowing the server to deliver a list of dependencies that need to be loaded before the task, so we don't have to hard code values like in this example. But at that point, we are adapting our implant, our server to implant communication protocol, and our server to accommodate the issue of task dependencies. But we can make this work. Another option is the assembly resolve solution. The benefit of this option is that the implant stays the same. The communication protocol stays the same, and the server stays the same. Only the task has to adapt to load up its own dependencies. Assembly resolve is an event handler that we can register callbacks to. If any assembly fails to resolve, the assembly resolve callbacks are tried as a fallback. If we load the assembly within the callback and return the assembly object, execution will continue and succeed. Assembly resolve is a carryover from the .NET framework. You may be familiar with projects like Costura. Costura actually makes use of assembly resolve to embed all of your third-party assemblies. And we can use it in this scenario as well. So that wraps up our practical problems and solutions for .NET Core. All right, so up to now we've really covered all the benefits and some useful information for malware developers, but what if you don't really want to do a ton of development, but you mostly just want to use the existing capabilities that are already out there? Well, there is some, but not a ton. I definitely encourage folks to start thinking about actually doing the development they wish already existed. But let's talk about what does exist. Like we've already mentioned, we have a .NET Core implant called Brutes that is built into Covenant. So what built-in capabilities does this thing actually offer? We have the basics like who am I, ls, cd, cat, make directory, remove, copy, and process listing. The basic quality of life commands you'd expect to see in an implant. We also have some functional commands like assembly execution, and that is for .NET Core assemblies only, of course, shell commands, and file download and upload. That's really it so far. There's definitely a lot more to do to bring built-in functionality to Brutes. One opportunity for doing so might be the courseplate post-X library ported by Checkymandr. This has some relatively more advanced capabilities like port scanning, lateral movement, persistence, privilege escalation, and possibly even domain enumeration. Unfortunately, up to this point, .NET has not supported the directory service APIs that you may be used to in the .NET framework. So Checkymandr was forced to use a third-party library to support domain enumeration functionality. It seems like system.directory services is going to be partially integrated in .NET 5, so we'll definitely have to be on the lookout for that. It's worth pointing out also that courseplate is not built into Brutes by default yet, although it probably will be eventually. So you have to do a little work on your own to use this with Brutes. But it is very possible, as we'll see in just a second. All right, so at this point, you probably just want to see some of this stuff in action to make sure I'm not lying to you about how any of this works. So we'll do a quick demo to show you how Brutes work, how to use some of the built-in capability, and how we can extend that capability with courseplate by utilizing many of the tricks and techniques we talked about today. So we already have Covenant running and an HTTP listener up and running, we'll start out by generating our brute implant payload. We'll select the brute implant template, and we'll select .NET Core 3.1 as our .NET version, which is the only option for this implant. And then we need to select a runtime identifier. Remember, we can only compile this payload for a single operating system. This tells the compiler which runtime is going to be stuffed into our payload. So we'll go ahead and choose OS X. After that, we click Generate and give it just a second and hit Download to get a copy of the payload for ourselves. So I want to give you a little bit of a peek under the hood to see how all of this actually works. You can see on the terminal output that it's running some .NET compilation stuff on the Brute Stager project when we do that. Let's take a look at our Brute Stager project file. So you can see that we're targeting .NET Core 3.1. We're making use of both the publish single file and publish trimmed features that we talked about before. And down here, you'll see a list of trimmer root assemblies specified. What this allows us to do is to add additional libraries to the trimmed executable that the IL linker does not recognize as a dependency. This can be a shortcut to support particular tasks that you want to add without going through the hard work of juggling dependencies like we talked about before. But this is at the cost of file size. So I'd certainly recommend against using this too often. In fact, brutes will probably be losing many of these in the future to continue combating large file sizes. Okay, now that we've generated our payload, let's go ahead and execute it. You can see we get an implant calling back here. Let's go ahead and interact with it. You can see this is on a Mac system. Using the help command, we can get a list of the capabilities we have at our disposal. We'll go ahead and use the delay command to make things a little faster. And we can do many of the basic tasks we talked about before, like a who am I? We can list files. We can get a process listing. We can use shell commands. And lastly, let's say we want to use some capability not built in to the implant, like say a port scanner. And we want to make use of CoreSploit to accomplish this, since it already has that capability built in. How might we do that? Well, first we need to make sure we've cloned CoreSploit. I've cloned it and have it open in Visual Studio here. Need to make sure we build it. Let's see, built correctly. You can see these port scan functions and libraries here. So once we have CoreSploit built, we'll need to create our own project called Port Scanner that references CoreSploit as a dependency and makes use of its port scanning capability to do what we need. So you can see here in the referenced assemblies, we have CoreSploit. We'll talk about this part here in just a second. And you can see all we're doing is making use of the CoreSploit APIs to do port scanning. You'll notice here that we make use of assembly resolve, like we mentioned earlier. This is so that we don't run into errors when we execute this assembly on a target since the target has no notion of what coresploit really is. You see that we have to add an entry here for coresploit, as well as a couple dependencies that coresploit itself has to accomplish this task. So when we build coresploit, we can copy out the base 64 bytes of coresploit, and we just copy it in here to make sure it resolves. So let's go ahead and do this. First, we need to make sure we build the port scanner. Then we can use the assembly command to go ahead and execute this. And we'll just go ahead and scan localhost port 22. And success. Hopefully this ties together a lot of the different nuances that we've been talking about that you have to consider in .NET Core, as well as gives you an idea of the real potential for using this in offensive operations. So we haven't really touched on defensive measures to combat .NET Core yet. I know it's a bit of a faux pas to provide just a single cursory slide in relation to defense in an offensive talk nowadays, so I hope you'll forgive me for doing so. On one hand, I hope that the offensive knowledge is valuable and informative in its own right, even for defenders. And I also believe that the topic of defense and detection when it comes to .NET Core deserves a deep dive all of its own. But for now, I'll leave you with these few thoughts. First, make use of the visibility sources that Microsoft provides you with. Make sure your anti-malware provider utilizes AMSI. Yes, I know it can be bypassed, but that almost doesn't matter. Attackers won't all be smart enough or diligent enough to do this all of the time. And even if they are, the bypass itself can be detected by AMSI. So there's really no good reason to not make the most of this opportunity as a defender. And ETW might become an even more important source of visibility for defenders. ETW will log all of the assembly namespaces being executed. If this information is collected and centralized, it can become a rich source of data, analyze and hunt for malicious behavior. And feel free to use brutes and coresploit as the first signatures to test against your logs. Seriously, we won't be offended. Please use everything we write as an opportunity for detection. You shouldn't rely on tool-specific detection measures as a silver bullet, but it can be a first step. Beyond signatures, like I've said, please start collecting and centralizing your ETW logs. This will be a great source of information in the future. Additionally, some of the unique features we've talked about today could be interesting research topics worthy of investigation on the defensive side. For instance, can we automate the process of distinguishing the difference between a published single file PE versus an ordinary unmanaged executable? If so, we could take that a step further and actually identify the user created assembly that's embedded inside a published single file executable and analyze those. These are a couple of topics that I certainly am interested in researching on the defensive side, but please feel free to beat me to the punch if it's something you would like to pursue. And finally, don't fight the wave of .NET Core. Don't go back to your employer saying that you heard a talk about .NET Core malware and how bad it is. And as an organization, we need to just prevent it from being installed or run anywhere inside our network. That's just not the right approach. .NET is used for legitimate software. It's going to be used. We have visibility sources for .NET. Preventing the newest types of software won't do us any good. Attackers are just as happy to use the unmanaged C implants that they've had laying around for years if you're really trying to prevent them from using .NET. It's really just not worth the fight. We have to adapt to the changing software landscape and learn to detect where attackers might pivot to next. If an organization acts now, they really will be ahead of the curve. .NET Core malware is still very much at the beginning of its its utilization curve, so defenders definitely still have an opportunity to get the jump on attackers. In conclusion, if I could pick just a few things for you to take away from this talk, it would be one, that .NET Core is about to become much more prevalent. .NET Core is the future of .NET. .NET 5, which is set to be generally available any day now, very likely will be installed by default on the latest Windows operating systems, I'd guess by as early as early 2021. .NET Core includes some key features like publish single file and publish trimmed that can be enormously useful and eliminates the need for .NET Core to be installed ahead of time. Practical issues like file size and dependencies are solvable. .NET Core is just very promising for malware development. As developers, we get to make use of the latest APIs like assembly load context, async primitives, and many others. We get cross-platform implants. Visibility issues can be taken care of with bypasses, just like in the .NET Framework. And in most cases, it's very easy to port the existing .NET Framework tradecraft that we already have. And finally, there's some experimental runtimes like CoreRT that are worth investigating as well. As a reminder, I am available for questions down in the chat right now. And if you want to join the conversation about these topics after today, I'd recommend joining the Bloodhound Gang Slack group, which is a free general InfoSec discussion group. And we have a couple of channels where this topic is being discussed, including the Covenant channel and the Stay Sharp channel. Feel free to use that link to join. Besides that, everyone, thanks for joining.